Yo, back with more Regents review for the August 2015 Chem Regents. And do I have the webcam on again? Oh, yeah, look at that. There's me. This is me. Okay, let's get back to it. Let's see what we're up to. Oh, okay, we are up to written response part 66. So 66 through 68 are based on the following info. Okay, so let's try this. Let's see. Give me a new color. I'll use red. Yeah, red. Sounds good. Okay. The two naturally occurring isotopes of antimony are antimony 121 and antimony 123. The table below shows the atomic mass and percent natural abundance for these isotopes. So these are the highest abundance isotopes of antimony in Earth, or in Earth's crust. Naturally occurring isotopes of antimony. You have isotope 121, and the real mass is 120.90, and the natural abundance is 57%. The other isotope, antimony with a mass of 123, the true mass in atomic mass units or universal mass units, which is why you have that little U symbol there, is 122.90, and that makes up about 43% of all the antimony atoms on Earth. Continuing reading, antimony and sulfur are both found in the mineral stibnite, which is the compound that the ratio in the compound is there are 2 moles of antimony for every 3 moles of sulfur. So that rock, stibnite, is basically antimony sulfide. And since the rock is called stibnite, that's actually where antimony gets its weird symbol SB from. So an element can be named after the rock, the mineral where we find it in the earth. So to obtain antimony, stibnite is roasted. Well, that's funny. Roasted, heated in air. I think we know that, roasting. So you roast it, producing oxides of antimony and sulfur. So basically you separate, you decompose stibnite so that you can try to get the antimony by itself. The unbalanced equation below represents one of the reactions that occurs during the roasting. Let's look at the reaction. It says you have stibnite, which is antimony sulfide, plus oxygen. And basically you oxidize the antimony, you get Sb2O3, antimony oxide, and you get sulfur dioxide, which is a pretty nasty smelling, pretty toxic gas of sulfur. Okay, so number 66. The first problem says to determine the percent composition by mass of antimony in stibnite. And the good news is that they gave us the gram formula mass, also known as the molar mass of stibnite. Okay, so I'm going to review how they got the gram formula mass and how to find the percent composition. So even though they gave us the gram formula mass, I'd actually like to go over how they obtain that. So let me go over here. So first, we do need the periodic table of elements because antimony and sulfur are elements. So first, let me go to the periodic table. Okay. So first, let's check sulfur. Let's see if I can zoom in there. Okay, the mass of sulfur is about 32. Oops, so we'll round the mass of sulfur to 32. And antimony's mass is 121.76. I'm going to round that up to a nice 122. So again, sulfur is 32, antimony is about 122. Okay, so this is how you get the molar mass, or it's also called the gram formula mass of a compound. So let's go back to the question. So they tell us that stibnite is Sb2S3. So 2 antimonies and 3 sulfurs. So to get the gram formula mass, so they call it the gram formula mass, which also is known as the molar mass, because this is the mass of 1 mole. you just multiply the mass of the elements by how many there are. So let's do antimony. So there are 2 antimony atoms times the mass of antimony was about 122. So that's about 244 atomic mass units, U, little u. And sulfur, there's 3 sulfurs, and the mass of sulfur is about 32. So 3 times 32, that's 96 atomic mass units. So if we add those up, that's 6 plus 4 is 10. 9 plus 1 is 10, plus 4 is 14, and 2 plus 1 is 3. So the gram formula or molar mass of stibnite is approximately 340 grams per mole. And does that match with what they gave us? Yes, it does. Okay, so now that we have that, we're going to use the equation for percent composition by mass, which is on the back page of the reference tables, table T, which has all of our important formulas and equations. See, it says important formulas and equations. Okay, here it is. It says percent composition. So we have percent composition by mass. It's the mass of the part that you're looking at divided by the whole mass of something, and it's a percent, so times 100. So if we look at the question, it says, what is the percent composition by mass of antimony, not sulfur, in Sb2S3? So how much of the percent of the mass of stibnite is antimony's mass? So let's follow the equation. It's going to be the part divided by the total times 100. So if you notice, the mass of the 2 antimony atoms in the formula comes out to 244. And the whole mass is 340. So if we do percent composition by mass, that's going to be the mass of the part we're focusing on, which is 244, because they asked for the percent mass of antimony. And the whole is 340, and percent is times 100. So 244 divided by 340 equals times 100. About 71.76, so almost like 72% antimony. Approximately 72% antimony by mass. There you go. And that is how you calculate the percent composition by mass. Okay, let's get all this stuff out of the way and try one more. Delete. Let's try 67. In the space in your answer booklet, show a correct numerical setup. So again, numerical setup means show your math or you get no credit. So correct numerical setup for getting the atomic mass of antimony. I hate that they don't call it the average, because the atomic mass that's given to us is really the average. So if we go, see, there I am. So I'm still here. So let's see, the atomic mass clockwise. So yeah, these atomic masses given to us on the periodic table, they're really the average of the isotopes of the elements. Like if you pick up a handful of carbon, you don't know which carbon atoms you have. It's like going to the store and buying apples. Some of the apples are bigger, some are smaller. Some atoms have more neutrons and some of them have less. So you don't really know which isotopes you have in a sample. So you just get the average. So to get the average mass for, what did they ask for? The average mass of antimony. We're going to use that data table. So if you notice, they give us the real mass. That's what we have to use. So we have to use the real mass and multiply it by the percent abundance. So I'll work it out over here, what they want us to do in the answer booklet. So 120.90 and 57 makes up 57%, and 122.90 makes up 43%. So what we would do to calculate the average mass, let's see, are you going to continue down here for me? No? All right, so then clear the page. Okay. So this is for calculating the average atomic mass. So they said that the mass of one isotope is 120.90. So that's 120.90. And what we're going to do is multiply that by the percent. The only thing is you can't multiply by 57. It's a percent. You have to divide by 100, which means that 57% is really 0.57. So times 0.57. And we're going to add that to the other isotope is 122.90. So it's 122.90 times that percent abundance, which is 43%, which is really 0.43. So 0.43. So 0.43. And without even doing any math, we already got the credit because it says show a correct numerical setup, meaning even if you do the calculation and you get it wrong, if you show this math, you will get the point. There is another way to show this. Instead of dividing the percents by 100 to turn them back into a decimal each time, you can do it in one shot. Watch this. So if you do the mass of one isotope times its percent abundance, 57, plus the mass of the other isotope, 122.90, times its percent without moving the decimal. To fix this issue, we can just divide everything by 100. So you have two totally acceptable answers here, the top part and the bottom part. Those are both acceptable ways of showing the math, and you will get credit for both. Cool. And one last one. Why not? Let's do another one in this video. So delete. Okay. Complete the balancing of the equation in your answer booklet. Okay, so you know what? To make this easier, I will go to the answer booklet. But by the way, we have to pay attention to something here. It says using the smallest whole number coefficients. So basically what that means is that if you balance the equation and the coefficients you have can all be divided by a common number to simplify, then you would simplify. But I don't mess with that until I'm done with balancing. So let's check it out. The answer booklet. Okay, so they have the equation to balance, should be there. Okay, and where are you? There it is. All right, so I will go through this step by step. Okay. So it looks like they gave us one coefficient already, which is 2. So just like in math class, what I would do is you're going to distribute. So the first thing I do is look at the elements that we have to worry about. So we have to worry about antimony and sulfur and oxygen. So I'm going to make a note. Antimony, 2 times 2. So that's 4 antimony atoms. Next element, sulfur, 2 times 3. That is 6 sulfur atoms. The next element is oxygen, which is 2 oxygen atoms. Okay, so this is the reactant side. You have the product side. On the product side, I'm going to write the elements in the same order that I had on the reactant side. So I'm going to put antimony, sulfur, and oxygen. Even though they show up in a different order, this is going to make my life easier. Okay. So we have on the product side, I see 2 antimony atoms. Sulfur, I only see 1. And oxygen, I see 1, 2, 3, 4, 5. Okay. Here's what I would do. I see odd numbers. I see a 3, and I see a 1. And the odd numbers are annoying. So I'm going to multiply them by 2 and change them even. So watch. Let's take a 2. So 2. So now distribute. So 2 times 2, that's 4 antimonies. Cool. 2 times 3 oxygens is 2 times 3. My brain stopped. That's 6. And again here though, I see 1 sulfur, and I know that I need 6 sulfur atoms. So you know what? I'm not even going to play this game. Let's just get that out of the way. 6 times 1 is going to give me 6 sulfur atoms, just like the other side. So far we have 4 antimony, 4 antimony. 6 sulfur, 6 sulfur. The only thing is, now we have 2 times 3, which is 6 sulfurs, and now we have 6 times 2, which is 12. So that's a total of 18. That's 18. Oh no, what am I doing? Sorry, 6 sulfurs. This is oxygen. 2 times 3 is 6. 6 times 3 is 12. Sorry, that's 18 oxygen atoms. If you notice, I left oxygen, the element, I left it to the last step. You want to leave the elements to the last step because, well, they're by themselves. If you multiply a coefficient in front of the compounds, you're changing the number of more than one element. So here, we need 18 oxygens. 18 divided by 2, that's 9. 9 times 2 is 18. There we go. That's the balanced equation. So it's 2, 9, 2, 6. Can we multiply? Can we simplify by dividing those? No, because they're not all divisible by 2 and they're not all divisible by 3. So there we go. So if I make that nice and neat, 2, 9, 2, 6. So I can make that neater. I'll delete all that. So it's 2, 9, 2, 6. There you go.